So what we want to talk about now is uniform circular motion. Clearly, this is two-dimensional motion, that you have something, it's in a circle, it's got some radius here, and this object is moving around with some velocity v, and so the position, the x and the y position keeps changing. And so as the x and y position changes, then it's obviously moving with changing x, changing y, so two-dimensional motion. So that's why it's in this chapter. So to describe this position, we can imagine a vector r, okay, and vector r has, length r, and is at some angle theta. Now let's say theta can change. So theta changes at a constant rate. And so we're going to say that theta is a function of time. Okay, omega t. So that's a lowercase Greek omega, not a w. So when we think about theta, we think that this is an angle, okay? And so d theta dt is omega, and so that's angular velocity. Well, if omega changes, then a d omega dt is going to be alpha, and so that's going to be angular acceleration. Now, you notice that this relationship here is exactly like x, v, and a, where v is dx dt and a is that. So that means that we could then say that the relationship here for theta is theta naught plus omega naught t plus 1/2 alpha t squared. So omega, the derivative of that is going to be omega naught plus alpha t. Okay, now we'll get back to this later on in the semester. For right now, we're going to assume that omega equals omega naught is a constant. So we have constant velocity. So in other words, that would mean that the angular acceleration is 0. Okay. And so if we assume that the initial angle is 0, then we can just say that theta equals omega t. Now, if x, if we want to find out what is the x values here, so this thing is some r, okay, it's got some x and y components to it. So we have an rx and an ry, okay. So Rx is just going to be equal to R cosine theta. It's supposed to be in R. And then Ry is going to be R sine theta. So this is going to be R cosine omega t. And that's going to be equal to R sine omega t. Okay. So we could then say that our vector r is r cosine omega t in the I direction plus r sine omega t in the j direction. Okay, now it can change. Now we're going at constant speed, but r is changing. So r is sometimes over here, sometimes over here, sometimes over here. So r is sweeping out a circle right here. And so that means that r is changing. So the velocity vector is dr dt. And so if we look at that, then we have r. Derivative of the cosine is negative sine. The derivative of the omega t is omega. Okay. And so over here, we have r, derivative of the sine is the cosine, and omega comes out. Okay. Well, here's the other interesting thing. If you have a circle, and the distance along that circle, the arc length, well, that's equal to r theta. if you measure theta in radians. I always used to wonder why they created some weird term called radian. Why not degrees? That should be perfectly fine. Well, the idea is the distance all the way around a circle is 2 pi r. The distance halfway around is pi r. A quarter of the way around is pi over 2r. And so they got the idea that, well, why don't we just say that the distance that you go in an arc equals r times theta? Well, if you measure theta as 2 pi all the way around, pi halfway around, pi over 2, then that works. And so this is a way of measuring so if S equals r theta, then that's a way of measuring the angle right there. Okay, so that's why they came up with this weird idea of radians as a way of measuring angles. Well, in that case, you look at this and say, well, wait a minute, that would mean that if the distance S equals r theta, and we know that theta equals omega t, then ds dt, that's going to be v, that's going to be equal to, well, that's going to be equal to r omega, assuming that it's constant. So that means that this is going to be our velocity. Okay. So there we have velocity right there. Okay. Now, if we look at this again, we say that the acceleration is dv dt. Okay. So I do another derivative, that's r omega squared, the sine is the cosine, omega t, okay, minus r omega squared sine omega t, okay. And so you look at this and say, well, okay, that's cool, but I just thought that we had said that the velocity was constant. And yet now we have something that's not constant here. In fact, this changes. As omega changes, the acceleration changes. Well, let's look at something else interesting. This acceleration here is equal to minus omega squared times r cosine omega t I plus r sine omega t j. Well, that is just r. Okay. So what this means is that your acceleration is exactly opposite r. You just multiply omega squared. Okay. So in our circle here, now what does this mean? From the origin right here, this is r. Okay. What it means is that that's my r vector. It means the acceleration vector is like this. The velocity vector is perpendicular, because if you look at what you have, the sines and cosines, that's perpendicular. And so what happens is that means that in the first quadrant, r, x, and y are both positive, but vx is negative and vy is positive. In the second quadrant over here, then x is negative, y is positive, but Vx and Vy are both negative. Ax and Ay. Ax is positive and Ay is negative. So that means it continues this way. So the velocity keeps changing. So the magnitude of the velocity is constant. It doesn't change. But Vx and Vy are not constant. They do change. And so the acceleration turns out to be constant in magnitude. So the acceleration is going to be the minus omega squared r. So that's going to be equal to omega squared r, which is omega squared r. Well, it's a circle. So circular motion, r is constant. So the acceleration has constant magnitude. It's always pointed towards the center of the circle. So we call that centripetal acceleration. So that's always pointed towards the center of that circle. Well, what was the magnitude of the centripetal acceleration? Well, the magnitude of that was omega squared r. Okay, so what's this? Well, this is the same as omega squared r squared over r. But r omega is v, so this is v squared over r. And so you can imagine, you can say that centripetal acceleration equals v squared over r in terms of magnitude. And so that's going to be what we need to know about this. But now we've derived what the centripetal acceleration is. So centripetal acceleration always pointed toward the center of the circle because it's always perpendicular to the velocity. The velocity is always tangent to the circle. Since it's perpendicular to the velocity, you change the x and y components of the velocity, but do not change the magnitude of the velocity. So the velocity magnitude stays the same, but the x and y components change.